Okay, before I move on to Quicksort, I would like to talk about the time complexity of a merge sort. And for comparison, let's talk about one of the other sorting algorithms we looked at already, insertion sort. So we saw that the best case here was big gamma of n. So it only takes n time if the array is already sorted. So that's my lower bound on the best that I can do. Of course, I have to process every element of the array before I know that it's sorted. The worst case, though, unfortunately, for insertion sort, is big O of n squared, right? Because that's actually, as someone noted in class, that's if the array comes in backwards. Okay, so we have to actually sort it. It takes I steps every ith element we add, and that turns out to be n squared. The average case is also, unfortunately, n squared. Okay. So the question is, does merge sort do better? Well, it turns out merge sort is incredibly reliable and reliably better. So the best, average, and worst case are all O of n log n. Okay. So I just want to sketch out a proof for this to give you some intuition. So with merge sort, we're starting off with an array of length n. And the merging step, we certainly have to walk through. So we said we split this into two halves. And to merge those two halves at this level, it takes n steps. Okay. So the merging takes n steps at this level. We have to walk through all the elements in each halves. Okay, but actually, before we even get there, we have to recursively go down and let me get half of this in here. We actually have to recursively sort and merge these two halves before we can merge them together into the full n. So then we actually do, each one of these takes n over 2 steps to complete at that level, at these levels. But then guess what? These also branch off down into smaller problems. So before I can solve the n over 2 problem, I have to have solved the n over 4 problem. Okay, so and each one of those takes n over 4 steps. Well, guess what? Before I solve the n over 4 problem, I have to have solved the n over 8 problem, right? So how far are we going to go here? Well, at some point, we're going to have a problem of size 1 or 2, depending on where we choose to our stopping condition to be. So we just have to ask the question, how many times do I divide in half before I get down to a problem of size 1? Well, that is, yeah, so we're going to say dot, dot, dot. And eventually we're going to have a bunch of problems of size 1, which is the stopping condition. Okay, so eventually we're going to have a bunch of problems of size 1. Well, that's just the log base 2 of n, right? So answer, log base 2 of n. That tells me how many times I have to have n before I get to 1. That's a different way of saying how many factors of 2 are there in n. Okay? So what we find is the height of this is log base 2 of n. Okay. So that's log base 2 of n. So that's how many levels we need to go. That's how deep we need to go in the recursion before we reach the stopping state. The other thing you notice is that if you add up the cost of all the problems that are at the same depth of recursion, it's always n. So at the top, I have one problem that takes n steps. The next level down, I have 2 problems that each take n over 2. The next level down, I have 4 problems that each take n over 4. So the interesting thing is here, actually, if you add up the cost of the problems that are at the same depth of recursion, it always adds to n. So we can think of this as the total number of operations like the area of a rectangle, which has height log base 2 of n and width n, which is n log base 2 of n. And no matter what, we always do the same thing, and that's the reason that the best, average, and worst case are all O of n log n. Okay, so that is the time complexity for merge sort. Very reliable sort. You can always count on it being that time complexity no matter what. Okay, so let's move on to quicksort now and see how that does.